Hey everyone, so in the last video we talked about general solutions to differential equations. We're going to keep talking about differential equations. We're going to introduce the concept of a slope field. Now this is something that we are going to talk about. This is kind of a new topic. It's kind of a weird topic. It doesn't really fit in too much with the progression that we're going through, but it's something that's still very interesting to see. So a slope field is something that is pretty cool. It governs the shape of functions. So um, we're gonna look at some slope fields, and it's gonna be pretty interesting. I think this is an interesting topic, anyways. So what is a slope field? So a slope field is essentially for every point, for every ordered pair, x and y, we assign it a slope. So we are taking an x coordinate, so we're taking an x coordinate and a y coordinate, and from there we are spitting out some sort of slope, which we'll call m. We usually call that the slope m. If you remember in Algebra 1, you said y equals mx plus b. But essentially, we're assigning an ordered pair a scalar value. So this could technically be an example of a scalar field. Um, but what, yeah, so this is essentially a scalar field. But what's cool about this scalar field is that the scalar we are assigning to the point, it's not really a magnitude, it's actually a direction because it's the slope. So it almost acts as a vector field, although of course now we're not dealing with the magnitude of the vector, we're dealing with just the direction. So what does this look like? So we're assigning a point, so we're assigning an xy point with dy dx, and we're calling this a function of f of x and y, but we don't really need to. We're calling that function kind of the idea of transitioning a slope over to a point. So what does a slope field look like? Well, you could have, well, I guess I'll give a couple examples. You could have a constant slope field, so that look like this. These are a bit tedious to draw out, but it's okay. And anything that you draw through this slope field, it's just going to be a line. So anything governed by the slope field is going to be something with a slope of 0. You could also have a slope field like this. I don't know, maybe it goes something like that. Something like it falls off almost like a 1 over x curve. And then maybe somewhere in here you get like a circle of some sort. So there's another slope field. I'm not entirely sure what the equation is for this, but anything that goes through there, maybe it looks something like that. You get a curve like that, or you could get stuck in here. You could get a circle like that, or maybe you're coming in here, you go there, but then you get swirled in, and you keep going around. This is something that you'll explore a lot more in multivariable calculus. Um, how the paths of something through a vector field. This is a slope field, not a vector field. How something through a vector field acts. So that would be important in fluid flow, something like that. But it's also important in differential equations. So why is it important in differential equations? Well, we're going to do an example and we're going to determine just that. So let's do an example with electromagnetism. So the Kirchhoff law for circuits says that the um, L times the derivative of inductance with respect to, or inductance times the current derivative plus the resistance times the current is equal to some energy output voltage E, and that's a function of t. So we can write that that's a function of t. Okay, but as you can see, this is a first order differential equation that we've been dealing with earlier. So what I would like to do is I would like to plug in some values. Let's make a direction field for where our resistance is 12, and we have some sort of current of 4, and then we have some voltage of 60. So what we are going to get, inductance, L equals 4. So what we're going to get is 4 di dt plus, then we want R to be 12 plus 12I is equal to 60. Okay, so what we want to do is we want to isolate this di by dt. So we can find a function of I, we can kind of find out what it is in terms of, what di dt is in terms of I and t. We want to find a function of I and t is equal to di dt. Okay, so what we do is we're going to subtract 12i. So we are going to get 4 di dt is equal to 60 minus 12i. Okay, so now all that's left is to divide by 4. So that gives us di dt is equal to 15 minus 3i. All right, that's pretty. So now we have some sort of function in terms of I and t. So now we are going to make a function in terms of I and t. Okay, so let's draw a slope field for this guy here. So we are going to draw here function of I. We're going to have t there. We're going to have I there. Okay, so we want to see what this direction field looks like. So let's see, we are going to get something that looks a little bit like this. Of course, this is very hard to draw just because we've got so many lines to get in there. And in reality, this would be continuous. We would have, each little guy would get their own point. But unfortunately, I can only draw so much. Anyways, what it looks like is that as we're going through, we are going to be approaching some value of 5 as t goes to infinity. So we're going to be approaching some I value of 5. And our curves are thus going to look something like this. So we're going to get curves that asymptotically approach 5. And this means that the limit as t approaches infinity of I of t is going to be equal to 5. So that is what we would call an equilibrium function. So I of t being equal to 5 would be an equilibrium function. Okay, so if we wanted to verify this directly, we would get di dt would be 0, because if we differentiate, so we get I prime is equal to 0. So we get 0 plus we would get 0 plus, or well, no, we'll go from the other equation. 0 equals 15 minus 3 times 5, which is equal to 0, right? So that's a verification that we have an equilibrium solution there. So we can draw all of our functions, all of our functions here. They're going to come off, and then we could have one that passes through the origin. They're going to asymptotically approach this equilibrium solution. So that is what we do with these slope fields. Now, in the next video, we're going to talk about Euler's method, and Euler's method is another way that we can kind of deal with differential equations. That's a numerical technique. And after that, we're going to talk about separable equations, which is probably the most useful for physics. All right, so we'll be back, and we'll talk about that in the next one. Thanks for watching.